Okay, it's 5:30, so I'm gonna start sharing the presentation that I've prepared. All right, so we're just gonna get into the talk itself and start with kind of the introduction and so on. So this is a 30-minute long talk, but I'm happy to hang around for a couple of more minutes for any questions that people have. And in general, I want this to be as interactive as possible. So please do use the Q&A tool to ask whatever questions you want, or the chat tool that is present with this webinar tool, right? Cool. So yeah, as you guys know from the event page, this talk is on generative AI, and in this talk we'll be going into the science behind ChatGPT and MidJourney. So I guess everyone must have heard about these amazing new AI tools. So ChatGPT is much more popular, I think, than MidJourney, but they're both really amazing tools, and all of these tools are something that would not have been possible even a couple of years ago. And even though the technologies have been around for a long time, there's suddenly been an explosion in the applications of AI, and these are like really good examples of that. And yeah, it's just been amazing, and no one could have foreseen this, and no why these things work, right? People understand how they work, but no one really understands in a lot of detail why they work. And so today we'll be like sort of peeking behind the curtain and looking into how these tools actually work. So about me, yeah, I currently work as a staff ML engineer at Sharechat. Although currently I'm in India for a bit. And yeah, I previously worked at Meta for about 3 years in the ad sampling team as an ML engineer. And I graduated from IIT Kharagpur with a dual degree in computer science. And I also had a startup right out of college called Attention.ai. It was before like all these .ai domains were popular. And yeah, that was acquired by InShots. So yeah, that's a bit about me. All right, let's get into the talk itself. So basically, it's about two very different tools, ChatGPT and MidJourney. And with ChatGPT, we'll be going into like how it works. So starting from deep neural networks, I'm not going to go into a lot of detail on deep neural networks. We already know how they work. They've been around for more than 10 years now. So just a brief catch up on deep neural networks. Then transformers, we'll probably go into a lot more detail on transformers. What is the GPT architecture? GPT is general purpose transformers, and how that is applied to language modeling. And then what are some of the surprising powers of these GPT models, right? So they're originally used for some language modeling tasks, but they can do a lot more things, as we'll see. And then we'll talk about this open research problem on AI alignment, and which many people consider to be the most critical problems, like not just computer science, but science right now, because like if AI is not aligned to that poses like a civilizational risk for us. And then we'll be talking about some of the practical aspects of GPT, and particularly chatbots, like how do you add memory? Most difficult problems when you're trying to actually use these GPT models to do something. Then in part 2, we'll be going over MidJourney. So overview of all the modeling techniques that go into these models. So autoencoders, GANs or generative and diffusion models, and on how diffusion works. and condition these diffusion models for text to image generation. And if we have time, we can go into some cool applications or some demos and stuff. All right, so part one is on ChatGPT. Now, usually they suggest to have like an icebreaker, and this is what and actually I couldn't think about an icebreaker for this talk, so I just asked ChatGPT, and you'll be seeing a lot more of this kind of thing with ChatGPT, right? So yeah, welcome everyone. Before we dive into the fascinating world of generative AI, let me ask you, have you interacted with an AI that felt so human-like that it made you question whether it was actually human or not? And that's what we'll be talking about and MidJourney. So yeah, before we start, let's share our favorite science fiction movie or book that involves AI. It doesn't have to be dystopian. Usually all of these science fiction books are like, really sort of dystopian kind of worst case scenarios. But yeah, you can even share some happy examples. So while people are doing that in the chat, yeah, I'll just talk about GPT models. So you start from and then an evolution on that is and then there is transformers applied to language modeling or general purpose transformers, which is GPT. Then you can actually use these. So GPT models are usually trained just to do like sort of language generation. So give it like half a sentence and it sort of completes that. But you can actually train them to do a lot of different tasks. So that is something called Instruct GPT. And then you can get into like what's like, actually having sort of better alignment and sort of better user interface and sort of scale. And that's something that's ChatGPT. So starting from the very basic model, going up to like what you see working right now, and what are all the steps that go into each of these technologies. All right. So let's quickly go just do a small overview of deep neural networks or multi-layer perceptrons. So multi-layer perceptrons, as you know, on neural networks are just, models. So what is a model if you think about it, right? So like in machine learning, the way we solve problems is we have these data sets where you have like a bunch of examples. So you have like some inputs and some outputs, and these are the examples. And then a model is basically something that just takes in the input and generates an output. It could be anything, right? Like it's basically like, some process that takes the input and returns an output. That process could be anything. Like model is a very generic thing. And then so the key thing about the model is that it is parameterized, right? So that model has parameters that if you change those parameters, the model process changes in some way, right? So model could be simple as a linear model, like it's just a line, and line has two parameters like slope and intercept. And then you can learn those two parameters, you can fit them on the training data, and then that model learns to predict the output from the input, right? That's as simple as that. And so what this multi-layer perceptron is just like, instead of a 2-parameter linear model, this is a more complex model with lots of parameters. And you have like these layers of neurons. And each of these neurons takes some input, applies some parameterized mathematical process on it and returns some output. And then you can sort of stack them all together. Deep neural networks, right? So the key thing with neural networks was that earlier people used to try very shallow neural networks. So they used to just try one or two layer neural networks, but the key breakthrough there was actually trying more layers. And what enabled people to actually, get useful applications out of these neural networks was the computational resources to actually train uh, deep models, right? Models with multiple layers and loads of parameters, right? So that wasn't possible in the past, and with GPU-based training and all the advances in software and hardware, that became possible. And because of that, we have this entire revolution in machine learning. All right. Yeah, just feel free to ask any questions if you have, but I'll just continue. So then you have these simple deep neural networks where you have just layers of neurons, and these neurons are just applying some linear function. And then you also have some non-linear functions at the end of it. So linear function means like it's just weight times input plus bias, right? So very simple operation, but you have loads of these operations stacked together, and that gives you like lots of parameters to learn. And then if you throw a lot of data at it, it sort of learns really complex models that can do lots of interesting things. All right, now we get to transformers, right? So what are transformers? So transformers are more complex structures. So they are basically neural networks, but instead of simple neural networks that just have like input and then multiple layers and then output, you have more complex architecture here, right? Yeah, someone asked how are neural networks different from functions? They're not different, right? And it turns out that this function, like it's really easy to learn the parameters for this type of function, right? And theories on why this category of functions is good at learning things from data, types of functions. But yeah, it just cool. So then in transformers, like here you'll see lots of different things going on. So you'll see transformer block, it takes in an input and it gives out an output. And then there are lots of these sort of subparts here. And the feed forward part of this is actually same as the neural network that we were discussing earlier, right? So this type of neural net earlier, which is this connected neural network, or also feed forward part. Layer norm is nothing but a normalization. So that's just to make sure that all the weights are sort of comparable with each other, and none of these different feed forward networks actually, different sort of, right? So they want to make sure that all of them have a similar the computation. And then you'll notice like there are some skip connections here. So that's again another trick that is to have like these sort of skip connections. And that makes it possible for the gradients to sort of flow through the system, right? So if you didn't have these skip connections, what would happen is that, once you have like a really, really stacked neural network with lots of layers, the updates on each layer start getting smaller and smaller, right? So these skip connections actually give you an option of like that helps, right? So when you're fitting on some example, it can just skip all these layers, or it can go through them, and then both of those terms can sort of interact. So then you have And that's really the key part of the transformer, right? Self-attention, but just looking a more broader way into this transformer, you have like an encoder and a decoder. So you feed in the input, the neural network converts that input, it encodes it into a representation. Then that representation is used by the decoder, which then decodes that sort of latent representation into an output. Within these encoder blocks, you have like feed-forward neural networks, and you have attention and all those kinds of connections and layer normalization and all that, right? All right. So what is action, right? It's one of the key things that differentiates transformers from sort of, and a typical example here is a sentence, right? So transformers were introduced originally for machine translate, something, right? And then there was a paper that said that, attention is all you need. That was the name of the paper. As the title suggests, the paper said that, if you have like these generic transformer modules with attentions, they can do basically any kind of language task. So you see here, like you have a sentence about like the boy is holding a blue ball. So you see that, the subject is ball. And what are the words that are associated with that subject, right? So you have the word blue, you have the word holding, and then the word boy, right? So whenever you're doing any kind of these tasks, for a model to actually understand this, when it's at the word ball, it needs to not just also look at certain words, and it's not like, look at all the words, right? So if you see like their sentence, ball is the seven words for the subject ball are actually, the second, fourth, and sixth word, right? And even the second one is not that important. Maybe, blue is more important. So there are all these kinds of associations going on. So you can't just look at the last word and then predict the next word, right? You need some way to look at the entire history and pick and choose out of the entire history what is important for the current word that you're at, right? And that's exactly what attention does. Allows you to basically, in a parametric way, look back upon your history, right? So if you have a sequence and you're at some word in the sequence, so you're at some position in the sequence, right? So sequence is just a generic, it's a sentence, it's a sequence of words. You're at some particular word or at some position in the sequence, and you're looking back at the entire sequence, and then you're able to use the representation words or all the component sequence, add up like those weights in some way. So it's a weighted combination of the representation of all the elements of the sequence that came in before you. And you're able to combine that to get some sort of score, right? So like here you can see that, so if you have like a sequence and each, so you have this like, you are welcome, means like space or whatever, sequence. Each can be represented, like each of these words is fed into like the first, this sort of feed, right? This, so each word is converted into like some numbers or something, right? Like an embedding. this word into some numbers that may. So, and then once you're at a particular element of the sequence, it can look back at all the numbers, right? Query them, right? And use their weights to sort of compute some representation of from that. So that's kind of the key concept of transformers, right? So being able to dynamically look back into a history and pick and choose what is important. And how do you know what to pick and choose? That is parameterized. So you have these parameters that control, okay, should I look at all the 5 words? Should I look at only particular words? And then once you have samples, those parameters sort of automatically align according to understand that, oh, you're this word is boy, so maybe I need to look at 3 words before or something, right? And all of these things are sort of being trained at the same time. The embeddings are being trained at the same time. And also, like, which words you want to look at when you're at a particular word is being looked at, is being trained at the same time. And it's just that you throw it like loads and loads of text, and all of these parameters and weights sort of converge to sort of good values. And that allows you to actually encode like an understanding of the language, right? So that's my attempt of trying to layman's way. But yeah, I mean, that's sort of one thing to just take away from this nation is that transformers are able to dynamically look into the sequence history and pick and choose parts that are relevant for the current task. Right? And this is one of the difference between something like transformers and something like recurrent neural networks. So I don't know if you guys remember, but recurrent neural networks was the state of the art in language modeling about a couple of years ago. And there, what used to happen was you had these time rolled neural networks. So at each timestamp, you would feed like one word at a time. And all of these neural network blocks had some concept of memory. So they could sort of take in the context so far and store it in sort of a summarized memory, and then use that summarized memory with the current input to generate the next word, right? But what transformer allows you to do is at any point, look at the entire history, pick and choose whatever you want, and use that to generate the next word, right? So it just fed all of the inputs kind of at once instead of RNNs or LSTMs, which are fed one at a time, right? And then another interesting thing with these transformers is that for, like, let's say you're doing some sort of machine translation task. So you had some representation of the input that went into the transformers, and that representation was passed on to the decoder stack. And then what does it actually predict, right? So for each position, it predicts a probability for each word, right? So you can see here, like for each position, you have vectors of length, vocabulary size. And this vocabulary size is the entire vocabulary of whatever language you're targeting, right? So let's say you're doing English to translations, English to Italian translation. So this one is the entire Italian vocabulary, right? And it predicts a probability for each word in that vocabulary. And this is why it's important to have like, a restricted vocabulary, because if you have like millions of words, then it becomes very difficult to learn and also to predict, right? So it will predict the probability, like for first position, what is the probability for each word in the vocabulary, and then we can sort of pick and choose the words with the highest probability and consider that as output. All right. So then we get to sort of language modeling. So what is language modeling? Like, so you have this complicated transformer architecture that I just explained, but language modeling in a nutshell is just, feeding the neural network sort of incomplete sentences and asking it to complete them, right? So you predict, so, you just say like, today is Saturday, so you just feed it like today is, and the target word is Saturday, right? Or then you can feed it today and say the next word is, So you can just break down these sentences into like sort of groupings of like incomplete sentences and then the next word. And that's what it is trained to predict. So it's just trained to predict the next word given a set of words, which sounds really simple, right? You're not training it to do anything particular. It is just like, and it makes like a lot of data accessible. Like you can just scroll the entire internet, fetch like whatever English text you have, just throw that at the model and say that, from this English text, predict the next word from like, for each sentence or each part of the text, right? Um, and but it turns out that then if you train a model to do this, it actually is useful for a bunch of, you've trained this big model for the language modeling task, but then you keep everything the same, you just change sort of the last layer, right? And you can use it to do classification tasks, right? You can use it to do sentiment analysis, multiple choice answers, anything, right? So just by freezing, like if you, so the advantage of having this sort of very generic task is that you can train a really big model using loads of data. And then you can just freeze that, most of that model, just change like the last layer and train it to do whatever task you want it to do, and it will do really well, right? So that's the main advantage of language modeling, right? So now let's get into like what GPT can do. So GPT can store information, and that information is stored in the MLP layers, actually, right? So you have this very interesting paper where you take like a transformer architecture, and what you do is you sort of corrupt some of these intermediate blocks, and it'll give you like a nonsense output, right? But then you keep doing that, and at some point what will happen is, so you have the corrupted model and you sort of one by one you start uncorrupting it, and then suddenly you'll get like a good output, right? And that allows you to identify, okay, what is the part that was actually storing this information, right? So you can actually very surprisingly pinpoint like specific parts of the model that are storing information related to the topic, to the input that you've fed, right? So here, like you said, the Big Bang theory premieres on, and the completion is CBS, and then you sort of corrupt that, and then do this process, and then you understand like which part of this network is actually storing this association of Big Bang theory and CBS, right? And not only can you locate it, but you can even edit that part of the model uh, to actually get, to actually change the model's beliefs. So here what they've done is that Space Needle is in downtown Seattle, but they were able to change the model. So first they identified which part was associated with the city of Seattle in this transformer, and then actually add some weight to that to change that to Paris. And the model actually now believes Space Needle is in Paris. Not only that, you can ask it all kinds of questions like, if I need to go from Space Needle to Eiffel Tower, so it will say, oh, you need to take a flight, right? Or you can just, sorry, if you need to go from Space Needle to Eiffel Tower, you can just take a cab, and it'll give you like directions and stuff. So that's kind of a very interesting discovery about ChatGPT, about GPT models. Actually, we haven't reached ChatGPT yet. I know I set aside 30 minutes for the talk, and we have lots of things to cover, so I'll just try to go a bit fast. So yeah, so the next interesting thing is actually alignment. So now you have these GPT models, but how do you actually get them to do something useful, right? Because if you remember, like GPT models just predict like text completions. But if you want them to actually do some tasks like ChatGPT does, you need to sort of align them, right? And that is one of the main things that we talk about when we talk about alignment, but it also includes things like, uh, what are the guardrails on the AI? So, it doesn't become self-aware, or it doesn't give like really toxic responses, or it always does actions that are aligned with what humans want, right? So these are some techniques that can be used, and you can just refer to the OpenAI web page for these techniques. But it's basically like you train a reward model that encapsulates what your definition of reward is, like what is a good output versus a bad output. And then you can use that reward model to define a reinforcement learning problem. So, like, you can say that this is a reward I want to maximize. Now, you do something, and then, you know, and then the reward model will tell you, is that good or not? And that feeds back into the model, and then it sort of fuses that to fit into like a good reward model. Um, and the way the reward model trained is basically using human feedback. All right. Now, another interesting problem with this is actually, okay, if you want to create a chatbot, so finally you have GPT models, then you did this fancy RLHF thing to make them better aligned so that they can do tasks. But one of the most difficult things is actually adding memory to them. So how do they maintain a context of a conversation, right? So the way you do that is, you can just sort of have this buffer memory. So literally just take the entire conversation and put it in the prompt every time. But the difficult part there is, these GPT models have a token limit. And the more things you put into that, so there's already like a big prompt that you need to add to it to make it sort of aligned. And then if you keep adding the entire conversation to that, it just becomes like, just hits the token limit really, really fast. Really interesting things here that people have done is something called conversation summary memory, where you actually feed the conversation to another GPT model and ask it to summarize it. And then you use that summary, right? So this is something that, comes about a lot when you're building these GPT based applications. Is if you run into some sort of difficult problem, just use ChatGPT for it, right? So even if you want to build ChatGPT, like you can use ChatGPT for that, right? So you wanna make like a summary of a conversation. Yeah, just use that in another GPT model, and then use that summary prompt, right? So that was something that I thought was really cool about this, right? And then there's something interesting called Auto GPT, which can actually doesn't require to be prompt. You can just give it a problem, and it can do all of these things. So you can actually see like the kinds of commands that it can generate. So here you just tell GPT that, instead of being a chatbot, but you can also do these different commands. So you can do a Google search, you can do all these kinds of, it generates, you can parse it and really do those commands. So it's his website, you actually go, scrape that website and feed it back to the model. And if you do this kind of thing with GPT, it can actually accomplish a lot of complex tasks, doing the planning and everything by itself, right? So it'll by itself make a plan that, oh, I need to browse this website, summarize it or whatever, and then, use that to make a recipe or, whatever, right? This is one of the really interesting things with Auto GPT. All right. Yeah. So the next part of this talk is about MidJourney. And I had actually prepared like a lot of details on sort of different sort of models like GANs, autoencoders and but I think we may not have to all of that. So we should probably just talk about like diffusion models, because the idea here is really cool, right? So yeah, so diffusion models are one way to do sort of image generation. And the way they work is uh, you you have this multi-step process where you add, like, you take an image and you add some noise to it, right? Then you add some more noise, some more noise, some more noise, until you get like something that's just noise, right? And then you train a model to predict, like, given step one image, what is the noise in it compared to the step zero image. So the model is actually predicting the noise. It's not actually predicting the image, but it's predicting the noise. So you give noise and say that, okay, what is the noise step two, right? So if you do that with like enough examples, what a model, like, just random noise, and say, okay, take this random noise, predict the noise from it. So it'll predict something, then you remove that, then feed it back again, right? And you keep doing that with like multiple steps. And then ultimately you get like an image, right? And that image is actually something that is really good, right? It's like an actual image that is really high quality, right? So by just training the model to like predict noise, you can just feed it a bunch of noise and use that to generate an image, right? But then how do you actually do like text to image from this, right? So for text to image, then you can just condition this entire process use text embeddings. So you can use the text embeddings from the GPT models or any sort of transformer model into the model as well, right? In addition to predicting the noise, predict the noise using this text representation. And if you do that, then what you get is something that which is super duper cool, right? Yeah. So cool. So I think we are way over time, but I guess I have some questions. Yeah, there were some questions on attention, that attention is able to take into consideration all the relevant tokens. What's the point of having multiple layers of attention? Yeah, I think that's a good question, because think of it as sort of hierarchical levels of thinking, right? So you have something that just reads the embeddings and has some representation of that knowledge. Now, even that representation of knowledge, then you have another attention block that is sort of looking into this representation of knowledge and building another higher level representation, right? So it's like a hierarchical thing, right? So like the first hierarchy would be dealing with like language and sentence structure and stuff. The next hierarchy would be dealing with sort of semantics and all that, right? And then if you do stack it enough, you get to something that actually is able to do like higher order thinking, right? And but the actual, like, that's the intuition behind it, but the actual reason why we do that is because it works. As simple as that. And we don't really know why it works either. Cool. Cool, guys. So thanks a lot for attending this event, and sorry that it took a bunch of time. But yeah, I'll be sharing the presentation as well, and it has a bunch of more details if you guys are interested. So yeah, thanks a lot, and we'll see you for the next talk. Thank you.